Right now, there's this invisible force flowing all around you, powering the very device you're watching this on. We call it alternating current, or AC, and it literally runs our modern world.
You know, it's so easy to take for granted. You plug something in and poof, it just works. But the power that's pulsing through that cord isn't some simple, steady river. It's actually this incredible rhythmic dance of energy. And understanding that dance is the key to, well, understanding pretty much everything about our technological lives.
All right, so here's how we're going to break this down. First, we'll go right to the source, the generator. Then we'll get into the language of the circuits that control that power. After that, we'll see how all the parts work together in harmony, and finally, we'll uncover the one trick that makes AC so unbelievably useful. So, where does all this energy even come from? It all starts with generating an electrical force. And it's not magic. It's a machine, a spinning machine that's the beating heart of our entire power grid. So, at the very heart of it all, you've got this machine, the alternator. What it does is it spins a magnet inside a coil of wire, turning that physical motion into electrical energy. But here's the key part. Because it's spinning constantly, the force it creates isn't steady. It oscillates, it pulses. And that pulsing force creates what we call alternating current. Now, this is totally different from direct current, or DC, which is more like a steady stream of water from a garden hose. AC, on the other hand, surges back and forth, over and over. And this constant reversal creates that beautiful sine wave pattern you see. That's the signature of AC. And honestly, it's the secret to its incredible power. Okay, so if the current is always swinging up and down, how in the world we actually measure it? We could look at its peak, sure, but what's way more useful is its effective value, sometimes called the RMS value. Just think of it like this. It's the amount of AC power you'd need to get the same job done as a steady DC current, like making a toaster glow just as hot. So when you see 120 volts or 240 volts, you're looking at that effective value. That's the number that really matters.
Okay, so we've got our current, but how do you control it?
I mean, you can't just let it run wild, right? Well, that's where circuit components come in, and each one has its own way of telling the current what to do. Let's start with the simplest guy in the circuit, the resistor. In a purely resistive circuit, it just acts like friction. It gets in the way of the current, slows it down, and turns some of that energy into heat. And as you can see, the current and the voltage waves rise and fall together. They're perfectly in sync, like two dancers moving to the exact same beat. Now, things get a little more interesting with the inductor. You can think of it as having this sort of electrical inertia. It hates change. Imagine trying to spin a really heavy flywheel. When you first apply the force, that's the voltage, it takes a second for that heavy wheel, that's the current, to really get spinning. And that's exactly why in an inductive circuit, the current always lags behind the voltage. And then we have its opposite, the capacitor. It's all about storing and releasing energy. Picture it like a tiny, empty balloon. The very instant you start applying pressure, the voltage, the air rushes in at its absolute fastest speed. That's the current. The flow is strongest at the very beginning, before the balloon is even full. That's why in a capacitive circuit, the current actually leads the voltage. All right, now for the main event. What happens when we put all three of these components together, the resistor, the inductor, and the capacitor, all in one circuit? This is where the real magic of AC electronics really starts to happen. This is what we call an RLC circuit for resistor, inductor, and capacitor. And in here, you've got this fascinating battle going on. The simple friction from the resistor, the hold on a second effect from the inductor, and the let's go now effect from the capacitor. They all have to figure out how to work together. So, in this more complex circuit, we can't just talk about resistance anymore. The total opposition gets a new name: impedance. It's basically the grand total of everything fighting against the current. The simple friction of the resistor, plus these push and pull effects from the inductor and capacitor, which we call reactance. So, you see, impedance is really a team effort, or maybe a team competition. You've got the resistor's steady drag, the inductor trying to make the current lag, and the capacitor trying to make it lead. The end result of that whole tug of war is something called the phase angle, which tells us who won. Does the current overall end up leading or lagging behind the voltage?
And this is so cool, at one very specific, almost magical frequency, something amazing happens. We call it resonance. This is the exact point where the inductor's lagging effect and the capacitor's leading effect are perfectly equal and opposite. They completely cancel each other out. It's like in that tug of war, both teams are pulling with the exact same strength, so nobody moves.
And just look at the result. It's absolutely dramatic. At that one special resonant frequency, the total opposition, the impedance, plummets to its absolute minimum. And with nothing in its way, the current surges to its maximum possible value. This isn't just theory, by the way. This is exactly how you tune an old-school radio. You're literally turning a knob to adjust the circuit and find that resonant frequency for your favorite station. Okay, let's bring this all home. We're moving to our final section to see the real-world payoff for all this theory. Because all of these principles enable one of the most important inventions in human history. And that brings us to the transformer. Honestly, its genius is just how simple it is. You have two coils of wire near each other. The alternating current in the first coil creates a constantly pulsing magnetic field. This field then creates a new alternating current in the second coil. And get this, the two coils never even have to touch. It's all done through that invisible magnetic field. And here's the absolute game changer. The voltage change is decided by the transformation ratio. It's just the ratio of wire turns on the first coil compared to the second. If the second coil has more turns, the voltage goes up. If it has fewer turns, the voltage goes down. It's this simple principle that lets us crank up the voltage super high to send power across the country with very little energy loss, and then step it way back down so it's safe to use in our homes.
And that quote on the slide just says it all, doesn't it? This ability to easily transform its voltage is the #1 reason why AC, not DC, won the war of the currents and became the standard for our power grids. Without the transformer and the AC that makes it work, our modern electrified world just wouldn't exist. It's that fundamental.
So there you have it. AC literally built the modern world. But here's a final thought for you. Look around. Our world is filling up with things that run on DC power. Your phone's battery, your laptop, solar panels, electric cars. All of that is DC. So the great challenge now is bridging the gap between the massive AC grid that powers our world and the DC devices that are filling our lives. What does that future look like? Well, that's the next big electrical puzzle we all have to solve. Thanks for watching.